Sir, we all are presenters, I think.
Sorry?
Sir, I think we
Yeah,
can mute.
just a minute. We are doing that. Just a minute.
No, what did you say?
So like we are presenters, we can mute anyone. So that's what the problem was.
Okay.
Yeah, CRM, go ahead. You are a presenter now.
Yeah. Okay. So I think we this was covered in the last class. So just uh, I want to touch upon it. So this De Morgan's law, I mean, this is a statement which is given here, 1 and 2, and uh, just you can see what the proof is like. So essentially, how do you prove it? So you the way you prove it is that you basically show that this these two expressions are complementary. So for this to be complementary, you go by the definition. So their meets must be 0, their meets must be 0, and their join must be 1. So I mean, this is rather more important for you to understand. Once you know that this is the approach you have to take, then the steps are not so difficult. All right. So all right. Now let us go over to the next thing. This is where we are having some difficulty. So, um, so here we consider a lattice with mean element 0. Now, yesterday, of course, we said that 0 is joint irreducible. I have put a question mark here. Um, the reason is uh, in most of the places 0 is usually not said to be joint irreducible. So the exact I mean reason I did not have time to check. So this is something that we need to check, but let us look at this. So diagrammatically, what is the concept of joint irreducibility? All right. Joint irreducibility, the concept is fairly simple. So C is joint I mean C is not joint irreducible, but or let us put it like this: A is joint irreducible, C is not joint irreducible. It simply means that C can be expressed as the join of X and Y. Okay, but A cannot be expressed as the join of X and Y. In fact, uh, I mean, X and Y satisfy this condition. So in fact, if you write A, the only way you can write A is A equal to, I mean, you can write it as A join C or A join A. All right, A join A. Of course, you can write it as A join A, or of course you can write it as A join Z such that Z is less than or equal to A. That you can, I mean, this will work. So joint irreducibility simply means that you cannot write A non-trivially as the join of two elements. That is join irreducibility. All right. So that is captured. So there is a slight change in this definition. All right. There is a slight change in this definition. So that is the concept of join irreducibility. Okay. So here also you can see if if x and y are immediate predecessors of C, then of course C is the join of x and y. Okay, so A not equal to 0 is join irreducible if and only if it has unique. It is join irreducible if and only if it has a unique immediate predecessor. So that is A, which we said is join irreducible. All right, and this is the concept of atoms. So in this lattice, for example, this one and this one, these are atoms. All right, these two are atoms, and of course, any element can be expressed as a join of a set of atoms. Okay. Now, this is a very important property of distributive lattice. So if the lattice is not distributive, so diamond lattice, you have seen that the diamond lattice has another element in between here. So here you can write A as the join of, in many ways you can write x, y equal to join of, this is the join of x, z, join of y, z. So this is, in this lattice, of course, these three are atoms, and you can write this in many ways. So because this is not distributive. All right, and do you recall the pentagon lattice? So if you call this, if you just call this, E. So, do you think D has a unique joint representation? Well, in terms of atoms, let us just say. So yeah, so you could express D as you can express D as the join of C and E, and you could also express it as the join of B and E, right? You can also express it as the join of B and E. Of course, C here is not an atom. C here is not an atom. But C, if you wish to represent it as so now C can be this is if you try to replace C, C cannot be expressed as the join of other elements, though. That is one thing. So you can't just replace C. So if you try to replace C, you could of course replace C as C or B. So Yeah, but you can't just get rid of C because here C is joint irreducible. All right. So I mean, so this distributivity is a very important property, and as you can see, that in a non-distributive lattice, elements do not have unique joint representations. We'll see more of that later. So now, for a finite lattice, you can represent an element as as such an expression where these D's are joint irreducible. Okay, these are joint irreducible. So now, yeah, and if if any dj can be expressed as the join of di and dj for di less than or prec equal to dj, then you can drop you can drop di, okay, and make the representation join redundant. All right, you can make the representation join redundant. So this the representation of any element is unique up to permutation for a distributive lattice. So let us just look at that more formally. So let us say that some element A, let it have two such joint representations, okay, and then we'll see that I mean, one can from one representation you can move to the other. All right. So and this requires the lattice to be distributive. Okay. So so any Ci or Dj in this representation is less than this because this is the join of all of these. Okay, this is the join of all of this. So any element here, this is any element here, and this is well, any element here. So this relation will be satisfied. Okay, this relation will be satisfied. So now since this relation is satisfied, you can say you can write this. Ci will be the join of Ci and this. All right, and then you can apply distributivity. You can apply distributivity. Now, since each element is joint irreducible, so this, I mean, if you go by the definition of joint irreducibility, then this has to match one of these, right? It has to match one of these. It has to match one of these. So let us say that it matches one of these. All right. So if it matches one of these, then you know that Ci is I'm just calling it less than or equal to Dj. Okay, Ci is less than or equal to Dj. Now with a similar working, if you can also show that, I mean, if you write this as dj is equal to dj and this c1 or c2, that way. So similar working, you can show that dj is less than or equal to ck. So you have this relation, all right, and again, since these are irredundant, you require this to be equal. So now you have this relation. So Ci must be less than or equal to Dj, and Dj must be less than or equal to Ci. So this requires that Ci must be equal to Dj. So so you can replace that corresponding Dj in this expression as Ci. So in this manner, you can pair off all the Ci's with Dj's. So you can move from one representation to the other. So that shows that in a distributive lattice, any element can be expressed as in this form, in the irredundant irreducible as an irredundant irreducible sum. All right. So this is a very important property. Now, based on this, let us look at an important property of Boolean lattice. So let us say that you have an element A, and let us say you have let Z be its complement. Okay, let Z be its complement. So these are the usual properties which hold for a complement. All right. Suppose now suppose that A has a unique predecessor. Okay, so if B is the unique predecessor of A and B is not equal to 0, all right, B is not equal to 0. And yeah, so now what you can see is that because B is the predecessor of A, so you can see that the join of B and Z must be same as the join of A and Z, and that must be 1, all right. And this also you can see, because B is the predecessor of A, so B and Z, meet of B and Z must be the same as the meet of A and Z, and that will be 0. So that establishes that B also will be a complement of Z. All right. This also so what it means is that a lattice with an element having a non-zero join irreducible element as a predecessor will not have unique complements. And so now you know that you have already studied that in a Boolean lattice this is not the case. So that requires all non-zero join irreducible elements to be atoms. So this is the only place where you can have this atoms. This is the only place where you can have this elements. All right, and all other elements will be expressed as join of these elements. All right. Now we so we have seen where the atom should be located. We have seen where the atoms should be located. Now let us see what how a lattice can be built up from these atoms. Okay. So what you do is non-trivial atomic elements. Yeah, so this you have seen. Uh, these elements are present right above 0. So if you call this level 0, then you can call this level 1. So this is level 0. This is level 1. All right. So these are the atoms, and you can think of those as sets of singleton elements also. All right. Now you can join pairs of elements. So to start with, this is your starting point. This is your starting point. So so what you do is from level I, you can move over to level I plus 1 as follows. So you take pairs of elements which differ in only one place. Okay, so basically they differ at only one place. So to start with, all of these atoms, they differ in only one place. So you take, so you basically, so you can say this is say with respect to this. So this is say yi and this is say yj. Okay, so you are taking the meat of yi and yj. Sorry, you are taking the join of yi and yj. Okay, so this is how you can move from level I to level I plus 1. So you take two elements which differ in one place. Okay, of course in this so here if you wish to go from here to here, so here let us say this A join B and A join C, these two differ in which one? So they differ in only one element. So you can take the join of this and this. So this is of course the join of, and you find that I mean you can also if you take this and this, all right, if you take this and this, here also they differ in only one element. All right, so here also you get the same thing. You get A or B or C. All right, so that is how you can move from one level to another. So if you go that way, you can build up the elements layer by layer. Of course, we are started from 0 and we are building up the lattice using joins. You can also do it the other way. You can also start from the top and move down by combining these elements using the meet operation. But this is just the dual. This is just the dual. All right. So this is let us say the basic method of building up the lattice bottom up. And if you count the number of elements, so here you can see, I mean, this identity holds. So here you are having NC0, here you are having NC1 and so on, NC2 elements. So so the total number of elements that you will have, this sum is equal to 2 to the power n. So you can, why don't you take up a small exercise now? So why don't you build a lattice with 4 atoms? if you start with 4 atoms, A, B, C, and D. I mean, why don't you just work out in your notebooks? Now I'll give you, I mean, just to so that you can do it a little more easily. I'll give you one hint. So you can, I mean, if you look at this lattice, it is like this. All right, and then you're drawing it like this, so you can just this is your lattice. All right, now you had, so this was your 0 element. Now to build it bigger, I'm just doing it this way just to show that there's a copy, and maybe we can, so you can hopefully this is a better placement. So you are connecting this to this to this, and should be able to. Okay, let us just connect it straight without so much. All right, so now this is your say this is your 0 element. This is A. Let us this is A. This is B. This is C. All right. This is A. This is B. This is C, and this is D. All right. So now you can you can try constructing. I mean, this is just for your reference. It should work out on this, right? So why don't you just try to complete this? Of course, I mean, you will have You will have maybe over here I can just yeah. So what will be this element? This one will be join of A and C, right? And this element will be the join of A and B. So yeah, you please write down yourselves also. This element will be the join of A and B. All right. And then so what is this element? What will this element be? Can anyone tell me? Are you doing it? Please do it yourselves. All right. This is the join of B and D. So can you work out the other elements? So if we take this AC and AD, so they differ in one position. So what will be the join of, so this one will be the join of ACD, right? Then uh, of course this element as you have seen, this was the join of A, B and C. All right. This was the, oh sorry, here I have a problem. This is I made a, none of you pointed out. This is the join of A and C. Sorry, what is this? B and C. This is the join of B and C. I don't, yeah. This is the join of B and C. So, A, B, C. So here I should get, so what is this? So this is, if you consider this B and C, so B, C and C, D. So this should be join of B, C, D. All right. Join of B, C, D. What is this element? This element is the join of A, B, A, D. So A, B, D. All right. And yeah, and this is the join of, so so as you can see, this B, D, B, D. So I can join these two, so I get this is in fact the All right. So, using the stone construction mechanism, I am able to build this lattice. All right. Yeah, are you with me? Hello?
Yes, sir.
Yes, sir.
All right. So now is it, I mean, let us just take out an exercise. I haven't tried this. So what about the number of nodes at any level of the lattice? So you can, of course, these atoms are at level 1. All right. Atoms are at level 1. So I can just write maybe, this level is 1. All the atoms are at level 1. All right. All the atoms are at level 1. This is of course level 0. And all these are at level 2. All right. These are at level 2. And so on. So these are at level 3. So can you find a way to count how many? The question is, how many in can you count the number of elements in level L?
Sir, 4CL.
Sorry?
4 choose L.
Yeah, but how do you come to that?
Sir, we can take any L number of.
Okay, let me see. If you go by this construction, uh, can you give a recursive solution? Can you give a recursive solution? Yeah, I mean just
So let's say we had like n minus 1 and the number of
okay. What will be a starting
elements.
lattice? What will be a starting lattice? If you, I mean, you should be building up, isn't it? So
Yes, sir. We
what should
start.
be a, so let us say that if you start with B1, I'm just saying, uh, B1 is, say, let us call it, this is B1, all right. Then what does B2 look like? B2 looks like, this is, B2, right? Yes? Yes or no? Hello?
Yes, sir.
Yes, sir.
All right. So now I can say, let us say, if I write B1 0 is equal to 1, means this is the level, all right, and B1 1 is equal to 1. This is my base condition. Now, starting with this, can you move up? See here, oh, sorry. So just try. So sorry. So now, can you, so suppose I have BML. How can I express BML? Can you tell me? Any suggestions? Is it possible to express BML recursively? Hello?
Sir?
Yeah. Yeah, tell
Sir,
me.
Sir,
Yeah.
BML minus 1.
BML minus 1. Oh, I'm just
Yes,
writing down what you are saying. BML minus 1. Then,
Yes,
sorry. And anything else? Just that or anything else?
Sir, BM minus 1, L minus 1.
BM minus 1, L minus 1. So, okay. So just check whether just check whether, so yeah, or do you think it should be like this? Should it be like this? Is this more appropriate?
Yes, sir.
Huh?
Yes, sir. BM
Yes,
minus
sir.
1 comma L and BM minus 1 L minus 1. Yes, sir.
All right. And yeah, and maybe you can say equal to 1 for L equal to 0. All right. We can say 1 for L equal to 0 and this for L greater than 0. All right. Okay. So is this okay? Hello?
Yes, sir.
Does it look similar to anything that you have seen before? It's not surprising, of course.
Yes, sir. M choose L is M minus 1 choose
Yeah.
L plus M minus 1 choose L minus 1.
All right. So it also comes from the way you built up this lattice. All right. Okay. All right then. So, all right. So that is how you can build up a Boolean lattice using, you can call it stone representation or stone construction. All right. So far we have seen, we have studied this, yeah, I mean, as algebraic structures, as you know, lattices as defined as an extension of partial orders with some more properties, some more very interesting properties. So, I mean, if you just think of the geometric shape, yeah. If you just think of the geometric shape, okay. So so a partial order, I mean, without could look. It's more like a tree. I mean, of course, a lattice is also a partial order, but without those properties, a partial order without those properties is more like a tree. All right, or maybe we can just say that the partial order may look just like this. A lattice, on the other hand, looks like this. All right. And of course, I mean, this is a very rough, but I mean, this is what your lattice, or at least a Boolean lattice, looks like. Yeah. Of course, this is also a partial order. It's not that your lattice is not a partial order, but partial order without the properties of a lattice will look more like this. Or it could also look like this, I mean, for that matter. Yeah. Okay. Now, this is another treatment. I mean, while you know, this is one kind of treatment. Now there you have another formalization. You have another formalization based on Huntington's postulates. Okay. Now, what we'll just see is that this Huntington's postulates correspond to, I mean, these are postulates for something called a Boolean algebra. Okay, this is called a Boolean algebra, and what we have studied is a Boolean lattice. So what we will show is that the two are essentially the same. Or I mean, you can have a mapping. So this is the mapping. In fact, the mapping is given here. The mapping is given here. All right. This is the mapping. Maybe I should have put it below this. Okay. So these are the yeah. So yeah. So these are the laws of Boolean algebra. Okay. So Boolean algebra is I mean, defined by these Huntington's postulates. These are the four postulates. Four Huntington's postulates. I mean, so what we'll see is that from these postulates, you can come to you can come to Boolean algebra. Of course, what you are saying is that from a Boolean lattice, if you if you start with a Boolean lattice, okay, I mean this is also all right. So nothing wrong with this. So yeah, so if you start with a Boolean lattice, so this is your Boolean lattice, and if you so from this you can you can map this lattice to an algebraic system as follows. So this is your lattice, and you had this meet and join operations. So if you map the meet to a plus, join to a dot, so you get this algebraic system, and the complementation operation is basically this. So complementation operation simply maps an element to its complement, uh, satisfying these properties. Okay. So if I mean, because you have mapped join to a plus and meet to a dot, so if you map an element to its complement, then of course these will satisfy these operations based on the properties of the Boolean lattice. And now these are your Huntington's postulates. So you can see, in fact, from what you have studied in a Boolean lattice, you find that all these laws, with this mapping, you find that all these laws are satisfied. Okay. Do you agree with me? From whatever properties you have studied for a Boolean lattice, if you perform this mapping, you find that all these laws are satisfied, right? Yes or no? Hello?
Yes, sir.
All these laws, in fact, we have shown that all these laws are satisfied. Now, what you are saying is that you can, so we started with the lattice, and from the lattice it is we can show that you can come to this Boolean algebra, okay, which satisfies this Huntington's postulate. So Huntington's postulates will satisfy the properties of a Boolean lattice under this mapping. You can also start from here. Suppose you have not studied Boolean lattice at all. So you can also start from here. And what we shall show is that starting from here, you can also come to the Boolean lattice. All right. So that is what we'll just do now. Maybe we can take a break for 5 minutes. Is that all right? Hello?
Yes, sir.
Yeah, we'll just take a break for 5 minutes. I'll come back in 5 minutes. Pavitra, is that okay? Okay, all right. algebra to Boolean lattice. All right, so that is what you are going to do now. So let us look at some properties which we'll prove using the postulate. So these are called axiomatic proofs. Okay. So so these are this idempotence. So these are properties of meet and join. Okay. These are basically properties of meet and join. In Boolean algebra, these are called idempotence. All right. So these follow from the postulates which are given. Okay, these postulates are given here. So yeah. So you can write x or x in this manner. I think it is best you can just look at the steps. These are not difficult steps. So you can just look at the steps. Anyway, I'll just go through the steps so that, yeah. So you can write it in this form, and one is basically x or x bar, and then you can you can apply distributivity. Yeah. So this is distributivity in the reverse. Okay, so you are applying distributivity in the reverse, and this is what you get. So now you have corresponding absorption properties, and as you can see, these can these also follow. You can prove this in an axiomatic manner. Okay. So one such proof is given. Based on these, you can try out the others also. All right, you can try out the others also. So this is also you have some more properties. I mean, these properties hold for Boolean lattices also. So, but we are proving these properties axiomatically. So you can just see how we are. I mean, look at this. Okay. So if you look at this, if you look at this, so these there are the truth tables of and, or, and not. Okay, truth tables for and, or, and not. This for a two-element Boolean algebra, of course. We're looking at a two-element Boolean algebra. or a one-bit Boolean algebra. Now, associativity is a very basic property, but if you have noticed in it's not part of Huntington's postulates, but associativity can be proven. So this is a proof for the associativity of Boolean plus. So I mean, I'll just outline the steps. Okay, you can go through. So this is what we want to prove, right? Yeah. So this is we are calling this one x and the other one y. So we basically want to prove that x equal to y. This is what we want to prove. Of course, that is also being achieved at the end. X is equal to y. So the steps, so you know, with x and y, so then you consider ax, bx and cx. So what you see is that all of these, ax is equal to a, bx is equal to b and cx is equal to c. Okay. And then you also have these ay, by and cy. And then what we show is that this, you know, through this we are showing that yx is equal to y and xy is equal to x. All right. And this is a crucial link. So here we are using the commutativity law. By commutativity. So that is how you prove this associativity property. So commutativity is a property of it's a Huntington postulate. Okay. So that is how this associativity is proved for Boolean algebra. So you can also prove other properties like the uniqueness of a complement. You had a proof for that in the lattice, for a Boolean lattice, not all lattices. Here the proof is using the axioms. Okay, so these are various properties. I think not go through these. So
maybe
yeah.
So CRM. So what is the equivalent of stone representation here? Is there an equivalent? I mean,
no,
I'm just asking. I don't know.
No.
I mean,
See, stone representation gives us a way to construct a Boolean lattice. Okay. Now here what we have is here we I mean this as I can see is a 2-element Boolean algebra. So here k-bit Boolean algebra is basically you just do vector operations. Okay. you just do vector operations. So that I think the corresponding. I've not thought of that, but
Okay,
I
okay.
mean, if
But
you
I think it's not necessary also.
no, you can. I mean, if you think of, I mean, maybe we can
So basically, what it means is that the bitwise
yeah.
operations
So
can be
if you
extended to
have
a.
if you have a k-bit, I mean k-bit Boolean algebra. So I think these will be the atoms. 1 0 0 0, then 0 1 0 0 0, then 0. This will be the atoms. I mean, this relates directly to the sets actually. So you can say that this is a characteristic representation of a set. This is AK. All right. This is the empty set. This 0. This corresponds to the empty set. And all ones. That is all ones is basically you can say corresponding to A1, A2, sorry. It means all the elements. AM. These are say if you have M elements, so AM. This corresponds to all ones. All right. So if you go, I mean, this is isomorphic to the power set lattice. Power set lattice, which is also equivalent to Boolean lattice.
By Stone representation theorem.
With say M atoms. With M atoms. And of course, it also and a Boolean lattice with M atoms can be built by Stone construction. All right. I mean, this is what this is how
Okay,
I
see. Yeah. Maybe this is the equivalent thing. Maybe we can give can you give an exercise to the students? For example, so let's take this exercise. So let's call this as a carrier set. So this Boolean algebra you define on a carrier set. Let's say the carrier set is the set of all square-free integers. Or let me put it this way: the carrier set is like this. Take an integer n, which is square-free. Square-free in the sense that it's not divisible by a square number. It's not divisible by a perfect square. So let's take a square-free integer n, and let's take all its divisors. Let's take all its divisors. So can you define some plus and dot operator and complement operator and ask the question that is a Boolean algebra or not? So I give you a carrier set which consists of all divisors of an integer n, and n is square-free. So it's not divisible by a perfect square. So my question is, can you define a dot and plus operator and a negation operator so that this is a Boolean algebra?
Yeah. Okay. So basically, we can we'll put it in the second set of assignments. So
okay.
yeah. So I just like to draw your attention to the fact that the first set of assignments have been given. So let me just show you. I don't know whether you have noticed it, but yeah. So this is the first set of assignments. So a few questions have been given. So please do this and submit. So so you should submit by February 21.
Sir, is this a group assignment or individual assignment?
It is a group assignment, and the groups are defined here. These are the groups. All right. These groups are aligned to the groups in the lab, of course. Only one group, I think, maybe one of these groups. I had two groups with two people, so I combined them to form a single group. Otherwise, these are aligned to the lab groups. All right. Yeah, so you need to work out the assignments and submit this. And then, as you can see from this, also you will get some problems. So one was given by Pavitra Mitra now, and so here, I mean, you can see that we have worked out only some of the properties. So other properties you can work out. We'll give those as assignments. All right. So I mean, these are the things we covered so far. So the next one, I think, yeah, I think what is there? Yeah, so the next one is on Boolean algebra. All right. So yeah, so we can just start on this. So Pavitra, do you want to start on this or?
Maybe CRM you can start. So should we start today or should we wait? I mean, start today.
We still got a lot of time, half an hour.
And then maybe you start because I don't have the slides. Maybe you can start.
Oh, I have sent you the slides, but yeah. Anyway.
Oh, okay.
All right. Okay. So maybe we'll just do a little bit of it and then we can stop. So yeah. So let us just. In fact, I have given you this last assignment. It corresponds to this. So you can look at this diagram. It's a Venn diagram. We have got two sets. In fact, I can draw a simpler one also. So we can consider just two sets. So this is A and this is B. This is, so this is A intersection B. This is if I consider this, so maybe I'll just write them this way so that you associate them with and maybe this whole thing is all right. This is A intersection B bar, all right. And if you take a single one, A, and this is A bar, all right. So Yeah. So you can think of this as call it A, this is A bar. All right. What about this? Can you draw the structure of this? No, this is actually not correct. Sorry. This is not correct. This is really, this is A, this is A bar, this is 1, this is 0. This is the structure. All right. So can you draw the structure of this? Yes? Can you do that? Well, you have actually done it already. So let us look at this. This is really what it is. So here, if you call this I mean, there's no harm in writing it this way, but I just meant to write it. You can write it in any order, it doesn't matter. All right. So these are your 4 atoms. All right. So why don't you just compute these joints and see what you get? Okay. So you can in fact compute these joints and see what you get. I'll leave that as an exercise to you, but yeah. So these are your, so if you take 3 sets, of course, you get more regions. And as you can see, if you have, okay, sorry. So if you have m sets, the total number will be 2 to the power m, right? The total number will be 2 to the power m. Now, you can have many selections. So if you take, so some regions are shown. So 1, 2, 1, 2 means over here you can see this part. Okay, this is 1, 2. This is A intersection B, as you can see. So like that you can, and it has also been worked out for you. So using you can say Huntington's postulates or Boolean algebra. So you can actually work this out. So what I asked you to do, that is shown here also. Now if you take 1, 2, 3, 4, 5, so this gives you E. Okay. So what you see is that any part of this, you can. So these are your building blocks. You can say these are your building blocks. All right, and you can basically select these building blocks to get various other regions. I mean, you can make any selection. So you have a total of 2 to the power m building blocks. All right, you have got a total of 2 to the power m building blocks. All right, and how many possible selections can you have? Yes. How many possible selections can you have using this?
2 to the power n. 2 to the power 2 to the power n.
2 to the power 2 to the power n. So these are the, you can have so many selections, and each selection actually corresponds to a Boolean function. Each selection actually corresponds to a Boolean function. So, all right. So anyway, so this is, and these Boolean functions themselves can be constructed. Yeah, so this is how you can interpret. I mean, one way to interpret. Okay, so these Boolean functions can be constructed from the atoms. So these are your atoms. These are your atoms, as you can see. And of course, these are themselves Boolean functions. So these can be constructed using the Stone construction, as you can see. And we have, I mean, this A XOR B. I mean, you know that A XOR B is AB bar or A bar B. So it is really the join of these two. So we have also used, we have just given common, common representations to this, some of these joins. All right, and yeah, so some of these could be, simplified. Some of this could be simplified. Now, the interesting part is that, I mean, these are actually coming somewhere in between. All right, these are coming somewhere in between. And if you look at this, from this you can go either this way or you can come this way. All right. So if you come this way, you are, yeah. If you come this way, what you get, yeah. Someone needs to mute. Someone needs to mute. Yeah. So if you come this way, I mean, basically, if you look at this, this is really the join of, sorry, it's the meat of this and this. So we, yeah, please mute. Yeah. Oh, okay. Sorry. So yeah. So you find that these elements come as the meat of these. Now, in this particular lattice, you get it in a single step. But if you look at this lattice, you find that uh, it's not so direct. All right. So of course, just a minute. So here, of course, sorry, it's the same. I mean, structurally, it's the same lattice. So, I mean, if you go a step above, if you go a step above, so here you have only A, B, and A bar, B bar. If you have if you have A, B, C, and A bar, B bar, C, then you will not get this in a single step. You will get this in 2 steps. All right. Yeah, from these elements. So these elements, as you will see, these are called mean terms. All right, and as you can see, any Boolean function is expressed as I mean, these are of course atoms. So any Boolean function is expressed as a join of mean terms, as you have seen in terms of a lattice. All of these can be expressed as a join of mean terms. And just these elements, so maybe I can put them in a different color. These elements, these are called max terms. And you can also see by duality that any element in the lattice can also be expressed as a meat of the max terms. All right, can also be expressed as the meat of the max terms. So yeah. So let us just see. And these are called literals. So what you saw here, these are called literals. These are called the literals. All right. These are called the literals. So a literal is a variable A or its complement. All right. Anyway, these are again some ways of so a Boolean expression is a string built from literals and the Boolean operators. So this is more like a grammar for expressing Boolean expressions. Okay, so I mean, this is just to know some terms. So you have this fundamental product and a fundamental product involving all the variables is called a mean terms, and these are the atoms in a Boolean lattice. Okay. So a fundamental, now this is an important concept. So a fundamental product P1 is contained or included in P2 if P2 has all the literals of P1. All right. Then you say that P2 implies P1. It simply means that whenever P2 is true, P1 is also going to be true. All right. And then you have a sum of product expression it's either a fundamental product or a sum of two or more fundamental products. So I mean this is more syntactic than anything else. It's more syntactic. These are I mean some of the, but this one is important. This implication. So for example, AB implies A. So whenever AB is true, definitely A must be true. Okay. Or for that matter, AB also implies B. All right. And what we have seen is that De Morgan's laws. So I mean, this can be simplified, as you have seen that A is the join of AB and it's the join of AB and AB bar. So that could be simplified to A using this properties or laws. Okay, I think that's all for Boolean algebra.
Yeah,
So
I think CRM we can stop today maybe.
Yes. Yeah. Anyway, we have come to the end of the slides also. Oh no, there are some more. But anyway, we'll come to this later. All right. We'll stop here today. All right.